Okay, hello, everyone. It's my honor to be invited to give a talk. Uh, it's not easy to organize such a network seminar in such a large size. Thank the organizers and the coordinators for their hard work and contribution. I also would like to thank Professor Musleher for introducing me. During the past several years, we have done some joint works on hypnosis modules, and I sincerely thank him for his strong support. This is also our joint work, which was focused on the paradigm on the hypnosis modules. Before I give presentation on mathematics, I would like to show you photos. This photo was taken 2 years ago with Ilan for 1 week. I really had a good time and had a good memory. I met very nice people, and I realized Iran is a country with a long history. So hopefully the COVID-19 pandemic will be stopped as early as possible so that we can meet each other. So let's begin my talk. The first section is this talk. So let's begin with the first section. The pattern of positive semi-definite matrix. Suppose A, B are emission positive semi-definite. For simplicity, in the talk below, I just say that A, B are positive. The pattern of A and B is denoted by A column B, which is the product of three matrices. The middle part is the multiplier inverse of A plus B. Recall that the multiplier inverse of matrix T is a unique matrix X, which satisfies the following four equations. These four equations are called the Penrose equations. And if X only satisfies the first equations, X is called an inverse of T. Generally, such an inverse is not unique, but for the Penrose inverse, it is unique. The paradigm is so named because it's originally in the circle, electric circle, when two resistors are connected in parallel. In here, R1 and R2 are two resistors, and it's well known that the reciprocal or the total resistance equal to the sum of these two terms. And from here, we can get a formula for the total resistance. So it's very similar to the paradigm. So these two authors just make a generalization from positive number to positive semi-definite matrix. Now you may wonder why we just consider positive matrix. The reason is, suppose A and B both are positive. We have these important two range equations. And based on these two range equations, we can get another expressions of A and B respectively as these. So if X is any one inverse of A plus B, then from the previous equations, we can get the product AXB is exactly equal to the parasum of A and B, which means that we can replace the multiplier inverse with any one inverse of A plus B. Such property is very important because we can develop many properties based on these equations or from these two range equations. For example, we have these two properties. The first one states that the pair sum A and B is equal to the pair sum of B and A. Also, we can conclude that the pair sum A plus A and B is positive. There are many topics concern the pair sum. One topic concerns is perturbation estimations. Suppose A, B, X, Y are positive, and we are given two arrows. One is X, one is Y, that connect to A and B respectively. So an arrow can be induced in this way. It can be deduced from Anderson and Dolphin, their paper. They shows that such an arrow is positive and a non-bond of E established there as this one, which is product of two numbers. The first number is only related to the first two matrix, and the second one, and the second one is the norm of X plus Y. Here, we use the notation norm means it's a two norm, or also known as a spectral norm or optical norm. And you may wonder why is positive. In this theorem, Anderson and Dolphin prove the positivity of E based on this equality. They introduce a matrix R in this way, which equals to E minus the pair sum X and Y. This shows that the inner product of this one is always bigger than 0, which means that R is positive because the pair sum X and Y is also positive. So from these facts, we can conclude that it is also positive. An explanation of this theorem can be given with these diagrams. There are 4 resistors. They are connected in different way. The first diagram, they're connected first in series, then in parallel. And the second diagram just change the order. And this theorem says that the total resistance in the first circle is bigger, and the second one is smaller. So this explanation of the positivity of this matrix. Okay, so let's move on. Checking the proof of Anderson-Dolphin's proof carefully, we can find that the norm of X plus Y appearing in a bond can in fact be replaced by any norm of Z, where Z is any common bond of X and Y. And the importance is the less is Z, the sharp is the resulting bonds, because we have well-known knowledge about the norm of positive matrix. Suppose A and B are two positive matrices such that A is less than or equal to B, then the same will be kept for the norms. So in view of this knowledge, we can conclude that suppose Z is a common bond of X, Y, then its norm is also bigger than the maximum of the norms. So from these remarks, we can get this conclusion. I just remind you that in these bonds, it's just the product numbers. So naturally, there are 2 lines to impose that bond. That bond. The first line is to reduce the number, the first number. The second line is to reduce the second number. To deal with the first line, one method we call factorization. It can be stated as follows. Suppose R is given as a ball. Is it possible to construct suitable matrix AT such that R can be factorized in this way? In here, the middle part, that is the matrix S should be positive. Explanation is suppose R is decomposed in this way, then this matrix will be positive automatically. And to deal with the second problem, we should find some suitable common bond. One choice is A plus B. Of course, it's much better than A and B, so it's not a good choice. Another choice is C equals A plus B minus the person A or B, which is smaller than the first one. What else? Can we find another one which is even smaller than the second one? I think it is a good question. Also, it's a good topic. A cis-algebra approach can be employed in dealing with these two problems. Actually, there are some similarity between matrix and elements in a cis-algebra. For example, in matrix, we have emission matrix, have a term of emission matrix. And in the cis-algebra, we have elements, self-adjoint elements, and some other similarities. A standard reference on cis-algebra is a monograph written by Pedersen, published many years ago. I know that many of you should be familiar with the theory of hyperspace. Also, some general theory about linear operators, and the term of cis-algebras probably may not so naturally as that of hyperspace. So we can give another look in the general setting of system modules, because every cis-algebra can be considered as system modules if we choose the inner product in this way. So that's why we consider problems in the general context of hyperspace modules, because it turns out more naturally than cis-algebras. And there are many similarities between hyperspace and hyperspace modules. Of course, there are many other dissimilarities. I will show you later, soon. We have talked about the parallelism for two positive matrix. Actually, the parallelism has been dealt with in other settings. For example, Mitra Auden has dealt the parallelism for non-square matrix. Of course, some additional conditions should be added. Also, the parallelism for positive operators A and B on hyperspace or hyperspace modules are also dealt with under additional conditions that the summation of A and B is ranging or A and B is closed, and also other context. And the most relevant to this talk is the last one. Williams started the general positive parallelism for general positive operators on hyperspace modules. Now let's make a comparison between the settings of Williams and ours. At first, look at the context. In their setting, the study saying the underlying space is hyperspaces, and in our setting, we use hyperspace modules. Of course, I mentioned that hyperspace modules is one generalization of hyperspaces. The first one is the generalization And second one, they consider two positive operators, and now we consider tractable pair of adjuntable operators. I also want to mention that these objects also are the generalization of these objects. The main tools in their setting is a Douglas theorem. And in our setting, we use two tools. First is Douglas theorem, but somehow it's different. So we call the modified Douglas theorem. And we also use the well-known factorization, which is the polar decomposition. And in Feldman-Williams, they introduced the pair sum. Now we introduce generalization, generalized pair sum. So from the text, you can see that we have made some generalizations. I want to emphasize that some generalization is really not trivial, because I will show you many similarities between Hilbert system modules and Hilbert spaces. Okay, here's details. I list 6 dissimilarities. The first one is, of course, all these terms are true if we consider the case that the underlying space is Hilbert space. Now, let's look at things in the framework of Hilbert modules. First, a boundary linear operators between Hilbert space modules may fail to be adjuntable. Second one is a closed submodules or Hilbert system modules can be not orthogonally complemented, which means that there may be no trivial projection between Hilbert modules. And the third one is the polar decomposition cannot be dealt with for some adjuntable operators. And this fourth one is Douglas theorem is conditionally valid in the Hilbert module case. I will say this a little bit in more detail. And also we have other 2 terms. So if we consider the pair sum in the framework of Hilbert modules, some new phenomena may happen. Okay, so this is my first section. Okay, now let's move to the second section. I will say about the Douglas theorem. In 1996, Douglas established a well-known theorem. Now it's known as the Douglas theorem. There are 2 items in this theorem. Suppose A and B are 2 boundary linear operators on a Hilbert spaces. The first term concerns range inclusion. That is range. Range of A is closed in that of B. The second one concerns the factorization. Here, A and B is fixed, and C can be changeable. That is, A can be expressed as a product of B with other C. The third one concerns visualization. It states that the first positive operator is less than or equal to the second one. Of course, this condition is equivalent to a non-equality. And Douglas proves that all these 3 items are the same. In addition, he showed that if this condition is satisfied, then there exists a unique operator, which is known as reduced solution, which satisfies the following 3 conditions. Okay, so most relevant to my talk is the last term, which means that the reduced solution will satisfy this one and this one. So we just we use these 2 conditions to make some generalization to the context of the modules. Now let's look at the application of the Douglas theorem. Suppose H is a Hilbert space. T is a boundary linear operators. Since if we input this operator, then it's obvious that T star equals S star. So based on the Doxa theorem, the equivalence of between the two conditions, we can get an equation of two ranges. Note that this equation is always true for every operator T. So if A and B are two positive operators, and we put T in this way and plug this T into this equation, we can get an equation ranges immediately as follows. So suppose A and B are positive operators, then we have an equation ranges. From these ranges equation, we can conclude that the first range is included or is contained in this range. Also, the second one is also contained the third one. So from the equivalence of first two items of Doxa theorem, we can use this equation to get two reduced solutions, switch the two equations. Okay, so we have two unique operators which denoted by C and D, such that this condition and this condition are both satisfied. With the introduction of C and D, Philip and Williams introduced the parallel sign in this way. Okay? And in special case that if the summation of A and range, if range of A and B, A plus B is closed, then it can show that this parallel sign is exactly equal to the previous one I have mentioned for hot matrix. So this is the framework of Feynman of Williams. Now, naturally, we want to make some generalizations. For example, how to generalize their result to the case-effect modules. So one thing we need to consider is this equation. So one question turns out this one. Oh, sorry. Maybe I just speak like, oh yes, this one, okay? So as it shows, the main tools employed Feynman Williams for the parallel sign Doxa theorem. And one problem is that HBX modules and A and B do positive operators. Is it always true that this equation is solvable? Remember that in Feynman Williams context framework, this should be solvable. But unfortunately, we give a negative answer recently in our joint work. So if we want to make some generations, we need some new thing to be put into, okay? So I think the reduced is the same. So I just skip this part. Now let's look at the generalized Doxa theorem. In this joint work, we have this lemma. For every A, which is the adjoint operator, we show that the following two atoms are equivalent. The first atom is the crucial range of A star is solidly complemented in H. The second one is for every adjoint of C, if the range of C is contained range of A, then the system 2.2 is solvable. Okay, so so on the condition that the crucial range of A star is solidly complemented, the equation AX equals C is solvable for every adjoint process, while RC is contained in RA. So roughly speaking, if we want to use the Doxa theorem, we need to use additional condition that this condition will be satisfied. Okay. One problem I think is very interesting is is it true that we can replace reduced solution in atom 2 with a solution? Remember that in the Higgs space is always true, and this one is always true. So no other conditions. But unfortunately, up to now, we have no answer. So this is a problem. And I have mentioned to make some generalizations, we should another tool that is called polar decomposition. So let's briefly recall some knowledge about the Higgs algebras and the Higgs modules. Higgs algebra is a complex finite algebra, which is an illusion star satisfying an equation, non-equality, which is called C star inequality. And as in the case of matrix, we can introduce norm elements and self-adjoint elements or emission elements, also positive elements. And also we have some non-equalities for positive elements, very similar to the two norms. And the most important thing I think is the commutative Higgs algebra. And for example, suppose X is a compact hot space and A is a set of continuous complex value continuous function X, then this A is a Higgs algebra, which is commutative. If the algebraic operation and norm are endowed in usual way. And it's remarkable that the reverse is also true. That is, by gain-found transformation, we can conclude that every commutative, if it has a unit, then it is also equivalent to this form. It's somehow complicated. I just mentioned that every unit commutative Higgs algebra turns out like this one. Okay, so this is commutative. And suppose a Higgs is not commutative, then we can deal things in local way. That is, suppose X normal element, or more specifically, if X is self-adjoint, then we just consider Higgs algebra generated by X. Then this Higgs algebra is commutative. So we can use the serial commutative, and then we can look things as like functions. Roughly speaking, we can join two subjects. One is algebra, another is calculus. So we can set up bridge between these two subjects. So it's the main idea. So if we consider the self-adjoint, everything will seem to be more easy because function is easier to be computed. Okay, so let's move to the Higgs modules. Higgs modules is a natural generalization of Higgs space. The main difference between Higgs modules and Higgs space is that it takes inner product its value in Higgs algebra, not in strictly in Higgs complex field. So here's definition. I just want to mention that the first atom, the third atom, and the last term turns out to the same as that in the Higgs space. But the second term should be new. And for the last term, I want to mention that in here, the inner product of X and X is actually not a number, which is the positive number in the given Higgs algebra. And like in the case of Higgs space, from these four conditions, we can get the well-known Kerr-Schwarz inequality. And based on the Kerr-Schwarz inequality, a norm can be induced in this way. And if the inner product A module is complete with respect to this norm, then this model is called Higgs module. Usually, we just consider right model. Okay, so in here, Y is taken in E, and A is taken in A. This is the right model. Of course, we can also count the left model. And suppose A, H, and K are two Hibs modules, and given T is an operator which is operated from H to K, and if there is another operator which is denoted by T star from another direction, from K to H, such that this well-known equality are satisfied for all X and Y, then we call T is adjuntable, and this T star is called its adjuntable operator. And I want to mention that there exists some operators which is not adjuntable. So we use this notation to denote the set of all operators such that which is adjuntable. And if T is a adjuntable operator, and we use standard notation, one is RT for its range, and NT for its null space. There are two references for his modules. One is written by British mathematician Lance. Another one is written by two Russian mathematicians, Majlov and his colleague. Okay, so this is the basic knowledge about the modules. And the most relevant to my talk is a concept of orthogonally complemented submodules. Suppose M is a closed submodule or Hibs module H. M is said orthogonally complemented if H is the summation of M and its orthogonal part. In this case, there is a projection from H onto M, which is denoted by PM. Okay, and there are cause some difference between Hibs space and Hibs modules. We can show that there exists two projections P and Q on certain Hibs module H, such that none of these four closures are not orthogonally complemented in H. I just give for the time limitation. I just give the proof. So it's quite a difference between Hibs modules and Hibs space. Now we talk about the polity composition. Let H and K be two Hibs modules. From now on, I just mentioned that everything is Hibs modules except the last part. Okay, and for every adjuntable operators, it can be shown that there exists at most a partial isometry U satisfying these two conditions. And if this U is satisfied, exists, then we call this one is a polity composition of A. I want to mention that in the finite case or for Hibs spaces, this condition is usually replaced by this one. It turns out much simpler than this one, but it's not true in Hibs modules. Some counterexample can be constructed, which shows that this condition is satisfied, whereas this one is not satisfied. So we should pay attention in the Hibs module cases. The second condition is this one rather than this one. Now we have this property, this lemma. In our non-joint work, we have this lemma. This lemma gives the non-specific conditions for the existence of the polity composition. Okay, and once I want to mention that, suppose A has polity composition, then we have two equations of the ranges, and if a polity composition of A is given by this, and we can show that A star has the polity composition, which is represented in this way. Okay, so we want to know whether this is also true for other adjuntable operators. The answer is negative. we can construct some heterogeneous modules such that none of these equalities is true. Okay, so this is the proof. Now we are ready to make a definition of the general person. First, let's look at the one definition. Let A and B be two adjoint operators, and we introduce an operator T in this way. The pair A, B is said to be tractable if T has a polar decomposition. Now, our next result indicates that that is TAB is tractable if and only if the following two conditions is satisfied. So this is full characterization of the tractability. And from this condition, these two conditions, we can use the general Douglas theorem. Now, suppose A and B are tractable from these previous two conditions, and the conditional Douglas theorem, we can construct it to reduce the solutions of these two equations. We call system because this X should be adjuntable. And with the injection of this C and D, now we give the definition of the general person in this way. So it's somehow similar to that of Feynman-Williams, but there's some difference because the Douglas theorem is not always true in Hibben module case. And also the polar decomposition is also not true for general adjoint operators. So we need another additional condition that the pair A and B should be tractable. That is, these two conditions have to be satisfied. Okay, with the introduction of generalized person, now we have some properties that are very similar to that of person. I list 1, 2, 3, 4, 5, 6 properties. The first one is concerned with positivity, and the second one, third one is concerned with the equality of positive elements, and the fourth and the fifth is concerned with range inclusions and range equalities, and the last one is concerned with the continuity. Okay, and also we have other properties, and in special case that, for example, if we are considered things in a Hilbert space, and suppose both A and B have the polar decomposition, then we can prove that the pair A and B is tractable if and only for the absolute value A star and B star is tractable. And in this case, we have this equation. So in this case, the general person is exactly the person of A star and B star. Okay, so we have seen some connection between the general person and the person. Also, we have another problems. I just take this one. And if we restrict our attention to positive elements, suppose A and B both are positive, such that the square root A and the square root B is tractable, then this general person is denoted by this. It's twice denoted by this, and they are called the person and harmonic mean respectively. Actually, many literature consider the harmonic mean in the context of positive definite operators or matrix, and in our context, we use more general context. So I think some generalizations can be made if we consider things in this context. Okay. Now let's move down. I want to say a little bit about two lines. The first line is how to construct common bond of two positive elements. Okay, and here is the main idea. We call the semi-commutative. Suppose A and B are two elements of cis-algebra. We call they are semi-commutative. If A and B can be expressed in this way, the middle part, Y and Z is commutative. You can see that maybe A and B are not commutative, but the middle part is commutative. So we call they are semi-commutative. And with introduction of semi-commutative, we constructed a common bond C in like this. Here, this is the element in the C subalgebra generated by Y and Z, because Y and Z are commutative. So this C subalgebra is commutative. And in the commutative cis-algebra, everything can be considered as continuous functions. So it is easy to prove that there exists at least a bond of Y and Z. So this is the main idea. And use this technique to our operators. We can construct a common bond of C star and BB AA star and BB star in this way, okay? And which is smaller, I already mentioned this one, which is smaller than this one. And we can prove that they are same if and only if the general person equals 0, okay? Of course, we should ask that the pair A and B should be tractable, okay? So this is the construction of the common bond based on theta technique. Of course, this one maybe is only lies in the smaller cis-algebra. It's not in the whole cis-algebra. And I want to say something. Just skip, okay? And things seem to be very complicated. For example, even in the case of H equals C squared, there are two matrices A and B such that AA star and BB star has no least common bond. We can show this, okay? Okay, just move on. Now let's look at the factorization theorem. This is our main result on this topic. Suppose A, B, X, Y are four positive elements of operators, and under some conditions, we can prove that A can be this operator R can be expressed this way, this factorizing this way. The middle part is the person with positive. So this is the main result in the factorization. Okay, so now we are ready to study the perturbation estimation. For the simplicity, I just talk about the matrix. In the matrix case, something is also true for in the general case, but I just focus on matrix because easier to be understood. Okay, so let's begin with the full matrix A, B, X, Y of same order. One idea to construct a bond of E is if alpha beta is positive, they're given, then we want to find another positive matrix Z such that alpha Z is greater than or equal to X, and beta Z also is greater than equal to Y. Because if such Z exists, then we can introduce this matrix. And according to the monotonic property of the parallel sum, so we can prove that this F alpha beta is bigger than E, therefore its norm is also bigger than E. So upon E, it can be given with this one. And if we can make some computation of this one, then a bond of the normal E can be derived. Now let's look at this condition. actually this condition can be changed in this condition. And I have already showed that we can use the same semi-commutative technique. So we can construct Z alpha beta in this one, and since we are considered things in for matrix, so a concrete form of Z alpha beta can be given in this way. It looks somehow complicated, but it really works. Why? Because we can give an upbound of norm E in this way. Here alpha beta available, so it is less than infinity in this way. And it looks somehow complicated, but we can use MATLAB to make some computations. And in special case, if we choose alpha and beta equals 1, then we can get a correlate in this form. This is a new bond by letting alpha beta equals 1 in this equation. And this original one obtained by Anderson and Dauphin. And I want to remark that this one is bigger than this one. This number is smaller than this one. And also this number is smaller than this one. So we can make improvement Anderson Dauphin's result. Okay, now let me show you 2 examples, numeric examples. First, for example, we construct A, B, X, Y as positive definite matrix in this way, because for every t, you can show that it can be shown that all these AT and BT are positive definite. And for this example, we can make some comparison between 3 bonds. One is obtained by Anderson and Dauphin. I have already mentioned almost half century ago in 1969. And this is a bond with the parameters alpha and beta. And this is no parameters, that is alpha and beta, both of them equal to 1. You can see that the relative error, this one is much bigger than this one. So the second one with parameter alpha and beta is much better than other 2. So this is the first example. I will show you another example. In some cases, we don't care about the parameters. This is exactly one example. If we choose A, B, X, Y, positive semiconductor matrix in this way, based on the MATLAB computation, we can show that the previous one is also relative error is also very large, and for the second one and third one, they are the same, which means we don't care about the parameter alpha and beta. Okay, so let me make a concrete remark. We introduce notation our checked pair of operators as well as that of generalization, generalized pair sum in the setting of adjoint operators on Higgs modules. Some significant results about pair sum known for matrix and Higgs space operators are extended to the case of generalized pair sum. In particular, a factorization theorem of the pair sum is proved, and the common bond of 2 positive operators is constructed in the Higgs module case. As application, the perturbation estimation for the pair sum of matrix are also dealt with. Now here's the reference. Okay, thank you very much.